USS Gerald R. Ford, a $13 billion nuclear-powered supercarrier, was removed from active service after a serious propulsion failure raised concerns about its ability to survive long deployments at sea. Today, something shocking is happening. The ship is finally returning to the water, but this is not a routine relaunch. It is the reemergence of a 100,000-ton weapons platform whose repairs were never fully explained, and the Navy is not eager to discuss what was really fixed. The $13 billion floating fortress comes back to life. The USS Gerald R. Ford is not simply a warship returning to service. It is a national asset engineered to dominate the world's oceans for the next 50 years. Stretching more than 1,100 feet from bow to stern and displacing roughly 100,000 tons when fully loaded, the carrier is larger than 3 football fields laid end-to-end and heavier than most skyscrapers built on land. Every compartment, deck, and system is designed to allow the United States to project air power anywhere on the planet without asking permission, relying on foreign bases, or slowing down for logistics. The $13 billion price tag attached to the Ford makes it the most expensive single weapons system ever constructed. That cost does not reflect luxury or excess, but the reality of building a floating city powered by 2 nuclear reactors, capable of sustained operations for decades without refueling. Those reactors do not simply push the ship through the water. They feed an all-electric architecture that powers sensors, weapons, aircraft launch systems, radar arrays, and internal networks that coordinate thousands of sailors and hundreds of aircraft at once. This ship is a power plant, an airbase and a command center fused into one hull. What separates the Ford from previous carriers is not just size, but intention. Older Nimitz-class carriers were designed around the technology of their era, then upgraded over time. The Ford was built to accommodate future technology that didn't exist when construction began. It generates roughly 3 times more electrical power than its predecessors, not to solve a current problem, but to avoid future limitations. This excess power allows the ship to integrate systems that did not exist when construction began and to adapt to weapons and sensors still under development. In naval terms, this is not just modernization, but strategic patience built into steel and wiring. One of the most visible examples of this shift is the replacement of steam catapults with the electromagnetic aircraft launch system, known as EMALS. Steam systems had served the Navy for decades, but they were mechanically complex, maintenance-heavy, and rough on aircraft frames. EMALS uses controlled electromagnetic force to launch aircraft with precise, adjustable power. This allows lighter drones, heavily loaded strike fighters, and future aircraft designs to launch safely from the same deck. It also reduces stress on aircraft, increasing their lifespan and reducing maintenance downtime. In combat operations, that translates into more planes available more often. Automation is another silent but critical advantage. The Ford-class design reduced crew requirements by approximately 600 sailors compared to older carriers, and this was not done by cutting corners. Advanced monitoring systems, automated material handling, and streamlined maintenance processes replaced manual labor where possible. Fewer sailors means lower lifetime costs, less strain on logistics, and faster response during high-tempo operations. In combat, fewer human bottlenecks can mean the difference between launching aircraft on schedule or losing critical minutes. All of this feeds into the ship's primary mission, sustained air dominance. The Ford is designed to generate up to 270 sorties per day, a significant increase over earlier carriers. This is not about one dramatic strike, but about relentless pressure through day after day, hour after hour of aircraft launching, recovering, rearming, and launching again. It is the ability to overwhelm adversaries through endurance, not spectacle. The Ford's return matters because it is not just a ship leaving dry dock. It is the return of a working aircraft carrier that the Navy depends on to control large areas of the ocean. This ship was built to launch air power, defend fleets, and support U.S. forces worldwide. But even the most advanced warship ever built can be crippled by a single failure. And for the Gerald R. Ford, that failure happened far sooner than planned. What went wrong? The failure that forced the Navy's hand. The problem revealed itself during sea trials in 2018, not through dramatic alarms or visible damage, but through data that did not look right. Engineers monitoring the USS Gerald R. Ford detected abnormal behavior in one of the ship's main thrust bearings. This component sits at the heart of the carrier's propulsion system, transferring power from the nuclear reactors to the massive propeller shafts that drive the ship through the water. It is not a pump or a valve that can be swapped out during a port visit. It is a foundational mechanical element buried deep inside the ship, and its failure carries serious consequences. As testing continued, the situation became impossible to downplay. The bearing showed signs of stress and degradation that exceeded acceptable limits. At low speeds, the system could still function. But at higher power levels, where a carrier must be able to sprint, maneuver, and respond to threats, the risk escalated sharply. Engineers understood what this meant. If that bearing failed completely while the ship was underway, it could damage the propulsion train, lock a shaft, or force an emergency shutdown. In the worst case, it could leave a 100,000-ton carrier unable to move under its own power. That scenario was unacceptable. A carrier that cannot maneuver is not just vulnerable but becomes a liability to every escort ship assigned to protect it. It limits strike operations, disrupts fleet formations, and invites adversaries to exploit weakness. The Ford was designed to operate at the center of a carrier strike group, not to be towed back to port under escort. The idea of risking a catastrophic failure at sea was never on the table. A full investigation followed, and the findings were blunt. The root cause traced back to machining errors during manufacturing by General Electric. On paper, the thrust bearing met design specifications. Under real-world stress, microscopic imperfections within the metal created weak points. These flaws concentrated stress in ways the component could not tolerate during sustained operations, especially at high speed. This was not a matter of wear and tear, it was a precision failure in a system where precision is non-negotiable. What made the situation more serious was the scale. The thrust bearing is enormous and integrated into the propulsion system in a way that makes replacement slow, complex, and disruptive. There was no workaround and no software fix. There was also no way to limit operations and hope for the best. The Navy faced a choice between accepting risk or removing the ship from service to correct the problem completely. For a platform meant to represent the highest standard of American naval power, there was only one option. Ordering the Ford into extended dry dock was not taken lightly. This was the lead ship of a new class, the most advanced carrier ever built, and it was being sidelined early in its operational life. On paper, it looked like a setback, but in reality, it was a demonstration of discipline. The Navy understood that a compromised carrier at sea is worse than no carrier at all. Reliability matters more than appearances. The decision meant over 15 months in dry dock, not just to replace a bearing, but to tear into the propulsion system, correct the flaw, and ensure it would never happen again. That timeline reflected the seriousness of the issue and the Navy's refusal to cut corners. The Ford would return to service only when it met the standard it was built to represent. But fixing the problem would require one of the most precise and demanding shipyard operations ever attempted. Locking a 100,000-ton warship into dry dock. Getting the USS Gerald R. Ford into dry dock was not a simple matter of steering it into a space and shutting the gates. It was a meticulous engineering operation where every movement was planned, rehearsed, and monitored in real time. Tugboats surrounded the carrier like precision tools, not brute force pushers with the job of moving a 1,100-foot, 100,000-ton warship into position with tolerances measured in inches. At this scale, even a minor misalignment could translate into structural stress once the ship's full weight came off the water. As the carrier crept into the dock, engineers tracked its position continuously. Laser alignment systems, reference markers, and ballast adjustments worked together to ensure the hull was centered perfectly over the support blocks embedded in the dock floor. These blocks were not generic stands, as they had to be placed in exact locations designed to carry the ship's weight without bending the hull or stressing internal frames. Once the Ford was in position, it was secured and stabilized before the next phase could begin. Nothing moved forward until every check confirmed the ship was exactly where it needed to be. Draining the dock was a slow, deliberate process. Over 100 million gallons of water were removed, not in a rush, but in carefully controlled stages. As the water level dropped, the hull emerged section by section, revealing parts of the ship that would normally never see daylight during its operational life. Propeller shafts longer than a school bus became visible, and massive rudders designed to steer a floating city were exposed. The scale of the ship was impossible to ignore once the ocean was no longer carrying its weight. This was the most critical moment. As the last water drained away, the entire mass of the carrier transferred onto the support blocks. Any error in alignment at this stage could have twisted the hull, damaged internal systems, or introduced new problems far worse than the original one. So the engineers had monitored load distribution constantly, checking that weight was settling exactly as planned. The shipyard did not just drain water, but carefully guided the Ford onto solid ground. With the hull fully exposed, technicians could finally access the propulsion system in a way that is normally impossible. The thrust bearings sat deep within the ship's structure, surrounded by layers of steel, shafts, and support systems. And reaching it was no easy feat. Seeing them in full context made one thing clear. These components were not designed for quick fixes. They were integrated into the heart of the ship, and replacing them meant disassembling and reassembling systems that had to function flawlessly once back at sea. The repair itself demanded extreme precision. Removing and installing the new bearing assemblies required alignment tolerances measured in thousandths of an inch. At this scale, being slightly off was not acceptable and would introduce vibration, wear, and future failure. This was not brute force labor but precision engineering performed on components weighing tons. As such, it needed specialized tools, custom fixtures, and constant measurement. Every adjustment had to be checked, then checked again. Throughout the process, nothing was left to chance. Every step was documented, inspected, and verified by multiple teams. Engineers knew that once the dock flooded again, there would be no easy access to correct mistakes. So the standard was absolute to ensure that when the Ford returned to the water, it had to be right the first time. After months of work below the waterline, the next challenge was to be reversing the process without undoing any of it. Rolling a supercarrier back into the water. Getting the USS Gerald R. Ford back into the water was not a moment of celebration. It was, after all, a controlled engineering operation designed to undo months of precise work without introducing a single new problem. The dry dock does not flood all at once as water is reintroduced slowly over several days, rising in carefully measured stages. This gradual process prevents uneven pressure from forming along the hull and protects the internal structures that were just repaired. At this size, rushing is how mistakes happen. As the water level climbs, engineers monitored the ship continuously. Sensors tracked hull strain, shaft alignment, and buoyancy in real time. The Ford must lift evenly off its support blocks, transferring its full weight back to the water exactly as designed. If one section rises faster than another, it could place stress on the propulsion system or shift internal loads in ways that were not intended. This meant teams watched for even the smallest deviation. This was the moment where months of work were either validated or exposed. When the carrier finally became fully buoyant, the focus shifted immediately to the caisson. This massive watertight gate seals the dry dock from the river and holds back millions of gallons of water. Removing it is a precise operation that depends on perfect timing, as water levels inside and outside the dock must match to avoid sudden surges or pressure differences that could push the ship off position. Only when engineers confirm the balance do they begin the process of clearing the gate. With the caisson removed, the Ford was no longer confined. But this freedom brings a new set of risks. A coordinated fleet of tugboats took control of the carrier and began moving it out of the dock at a speed measured in feet per minute. At this stage, the ship cannot yet rely on its own propulsion. The tug crews work in tight coordination, pushing and pulling in exact sequences to keep the carrier aligned as it transitioned into open water. There is no room for improvisation when handling a nuclear-powered ship of this size. On board, sailors and engineers had to remain on full alert. Even though the carrier was moving slowly, the systems are still being watched closely. Propulsion indicators, shaft behavior, and internal responses had to be monitored continuously, and any abnormal reading would trigger an immediate halt. The ship might be floating, but it was still under evaluation. This phase was still more about confirmation, not confidence. As the Ford cleared the dry dock completely, the scale of the moment became clear. A 100,000-ton warship that had been locked onto concrete blocks was now back at sea where it belongs. But this is not a return to duty. It is a return to testing. The repairs have passed the first and most basic requirement, which was that the ship can float, move, and respond as expected. But that did not mean that the carrier's journey is not over. Being back in the water is only the beginning of the proof process. Before it could rejoin the fleet, every critical system must be pushed, stressed, and verified under conditions that no dry dock can simulate. The Ford must prove that every repaired system works under real-world stress. Testing a warship like it was already at war. The first major test of the USS Gerald R. Ford began before the ship ever left the pier into the open sea. The Navy ordered a full fast cruise, a demanding evaluation where the crew operated the carrier exactly as if it were already deployed. Power systems were pushed to combat levels, communications networks ran non-stop, and damage control teams drilled as if fires or flooding were real. The goal was simple: prove that the ship could function as a warship even while tied to the dock. During the fast cruise, nothing was treated as theoretical. Sailors manned their stations around the clock and command teams processed simulated threats. Electrical load surged across the ship as systems were turned on simultaneously to replicate combat demand. The repaired propulsion systems were monitored closely, even though the ship was not yet underway. Engineers watched for irregular power flow or vibration that could indicate deeper problems. The Ford was being stressed from the inside out. Once pierside testing was complete, the carrier moved to sea trials. This phase was designed to remove any remaining doubt about the repairs. The ship was taken to flank speed, forcing the propulsion system to operate under maximum load. The thrust bearings that had once failed were now under the highest stress the ship could generate. The Ford did not cruise gently but accelerated hard, slowed rapidly, and repeated the process again and again. Tight turns followed. These maneuvers placed uneven loads on the shafts and bearings, simulating evasive action and high-tempo operations. Engineers monitored vibration levels, temperature changes, and power transfer in real time. Even minor deviations were logged and analyzed immediately. The ship was not just being driven, but was challenged to prove its reliability under pressure. At the same time, attention shifted to the flight deck. The electromagnetic aircraft launch system and advanced arresting gear underwent dead load testing. Instead of aircraft, heavy-weighted sleds were launched and recovered repeatedly. Each launch tested the system's ability to deliver precise force without overloading the deck or damaging equipment. Each recovery confirmed that arresting systems could safely absorb energy under controlled conditions. These tests were deliberate and unforgiving as the Navy did not accept partial success. Launch after launch, recovery after recovery, the systems had to perform exactly as designed. Only after repeated flawless results did officials authorize live aircraft operations. When real jets finally launched and landed, it marked one of the most critical milestones in the ship's return. Still, certification did not come quickly. Every major system in the form of propulsion, power, command, sensors, and aviation had to operate together at sustained tempo. The Ford was evaluated as a single fighting unit, not a collection of parts. Only when the Navy confirmed that all systems could function together under realistic stress did the carrier receive approval to return to the fleet. The message was clear. This ship would not be declared ready because of its cost or reputation. It would be declared ready because it proved itself. And while the technology dominated the headlines, none of this would have mattered without the people willing to carry the burden. The people who made the comeback possible. The success of the USS Gerald R. Ford's return was not built on steel and circuits alone. Shipyard workers logged over 800,000 man-hours just on the thrust-bearing repairs. These hours were not simple labor, as they involved long shifts in confined spaces, often below decks and beneath tons of hull steel, where precision and safety were equally critical. Every cut, weld, and measurement had to meet exacting standards, as a single error could compromise propulsion or misalign a bearing, rendering months of work useless. Workers operated under constant pressure, knowing that the world's most advanced warship rested in their hands. Engineers, machinists, welders, electricians, and inspectors functioned as a single, tightly coordinated ecosystem, where alignment tolerances were measured in thousandths of an inch. Bearings, shafts, and hull components had to fit perfectly, or the Ford's nuclear propulsion system could fail catastrophically under load. Each trade depended on the other, and communication was absolute. Decisions made by one team rippled across the entire repair effort, amplifying both responsibility and risk. At the same time, the carrier's crew remained assigned to the Ford throughout the extended dry dock period. Sailors maintained readiness through rigorous, continuous training, ensuring that skill atrophy did not become another hidden cost of the downtime. Damage control drills, flight deck simulations, and command exercises were repeated daily. Officers and enlisted personnel treated the docked carrier as a live operational warship, maintaining both discipline and institutional memory. Every action reinforced their readiness to return to active service immediately. Coordination between civilian shipyard teams and Navy personnel became a benchmark in large-scale maintenance operations. Safety protocols, inspection reports, and technical logs were meticulously integrated to prevent missteps. Engineers liaised with Navy operators constantly, ensuring that repairs not only restored capability but enhanced it. The collaborative effort reflected an industrial scale and efficiency that could only exist when government, military, and skilled labor operate in perfect synchronization. This made Ford's comeback more than a technical achievement. It was a demonstration of institutional discipline, national industrial capacity, and human dedication. Each bolt tightened, each test conducted, and each system verified was a testament to the combined effort of thousands who worked to restore America's cutting-edge power projection platform. With the USS Gerald R. Ford fully restored and its systems proven, its return carries weight far beyond the ship itself. It signaled renewed American naval dominance and the readiness to project power anywhere in the world. Why the Ford's return matters to American power. The return of the USS Gerald R. Ford was more than a technical achievement, but a statement of national power. One carrier of this class operates across hundreds of thousands of square miles, carrying the full spectrum of American air capability, without reliance on foreign bases or permissions. Its presence alone communicates deterrence, projecting strength that forces adversaries to account for U.S. reach, speed, and resolve. Commanders, allies, and rivals alike recognize that the Ford can respond to crises anywhere in the world, delivering sustained air power at a scale unmatched by any competitor. Beyond immediate operational capability, the Ford serves as a platform for innovation. As the first ship of its class, every system is a testbed for the 9 additional carriers planned to replace the aging Nimitz-class fleet. Lessons learned during its construction, operational trials, and post-repair testing directly inform future vessels. Each adjustment reduces risk, improves reliability, and ensures that future carriers are more efficient, less prone to failure, and more capable in combat conditions. The Ford is both a weapon and a blueprint for sustained naval dominance. Its versatility extends beyond power projection. Unlike land-based air forces, a carrier like the Ford can remain on station for months, launching hundreds of sorties per day without requiring host nation support. From humanitarian missions to combat operations, the ship is designed to operate continuously in tough conditions, maintaining readiness in every weather, sea state, and conflict scenario. The advanced automation and reduced crew requirements make sustained operations possible with fewer personnel, minimizing fatigue and maximizing operational tempo. Finally, the successful rollout from dry dock proved a critical point. Even the most complex warship ever built can be repaired, upgraded, and returned to full capability. The Ford's return signaled to the world that American naval power is resilient. Equipment failures, logistical challenges, or unforeseen setbacks will not compromise the United States' ability to dominate the seas. Every repair, test, and training exercise reinforced confidence in the ship, its crew, and the shipyard workforce that made it possible. In short, the USS Gerald R. Ford is more than a floating fortress. Its return demonstrated that America can build, sustain, and deploy cutting-edge naval power anywhere on the planet. The ship embodies technical innovation, human skill, and strategic foresight. Its presence is a warning, a reassurance, and a symbol. The United States will always remain capable of projecting power decisively, globally, and without compromise.